Assalamu alaikum, dear students. We're back with another video lesson. I hope you've been practicing well lately. If you remember in the previous lesson, we talked about the total acceleration, if you remember, and that is basically if we have tangential and centripetal acceleration, how do we find the total? And of course, we did talk about tangential, we did talk about centripetal acceleration as well, yeah? But if you're given these two together, how do you find the total? We said we're going to find the total by using Pythagorean theorem. And of course, tangential or total acceleration equals to the square root of centripetal acceleration squared plus tangential acceleration squared. That is to find the total or the magnitude of the total acceleration. And what did we use to find the direction of the total acceleration? We used tan theta. We said tan theta is basically equals to what? Equals to centripetal acceleration divided by tangential acceleration. And of course then you will find theta by using the tan inverse of centripetal acceleration divided by the tangential acceleration. And then, by the way, sometimes you might be given, let's say, as long as you're given the angle, let's say, you might be now required to use sine or cosine of the angle to find whatever that is required. So tan theta is not the only function that you might or you need to use. There is a probability, there is a chance that you might need to use sine or cosine of the angle to find whatever that is being required, whether it is centripetal acceleration or tangential acceleration. Very good. So we've covered all that. If not, please make sure that you go back to the previous video and watch it. Now, today we'll cover causes of circular motion, and that is basically the last section of Unit 1. Okay. So now the force that maintains circular motion, that is the concept for today. Now consider a ball of mass as the one that is in this picture that is being rolled in the air. So what happens if you have a ball, let's say, that has a mass and it's attached to a string and you're trying to make it move in a circle? And of course you can see here, once you're making this to move in a circle, you can see here at every instant this ball would have a different, let's say, velocity. When we say velocity, maybe the magnitude of the velocity or the tangential speed here, or let's say the angular speed, doesn't change, but what it changes is the direction. For example, at an instant here, the direction of the ball is towards, let's say, this way. Yeah? At another instant, it is this way. Let's say at another instant, it is downward. At another instant, it is this way. Yeah? So you can see here, the direction of the velocity keeps changing. Even if the value of the velocity, let's say, even if the magnitude of the velocity doesn't change, remember this, because the direction of the velocity is changing, so that means you have acceleration, yes? And of course, this acceleration we used to call centripetal acceleration, and it is always directed towards the center of the circle. Very good. And what was the equation that we used to use? We were saying acceleration or tangential acceleration equals to, not tangential, my bad, centripetal acceleration equal to tangential speed squared divided by the radius, or you can say velocity since we're talking about direction as well. All right, but remember this, when the object is moving, let's say, there is something else that keeps or tries to keep the object move in a straight line. And of course, that object or that thing is called inertia. So let's say here's the mass that what we have, yeah? Once you're rolling this mass in the air using the string, of course, now there's a tension here, we do know that, yeah? And then we said at every instant, the velocity of this would have a different direction here, yes? But then, all right, this mass here, or the object that you are trying to move or make it move in a circle, always try to or tends to move in a straight line. Why does it so? All right, that is because of something that is called inertia. You do know that inertia, or you've studied that, yeah? Inertia is basically try or resist, or tries to resist the change in motion. Because this object is moving, let's say, so here's the direction, inertia tries to keep it moving in a straight line, yeah? Because it is the tendency to resist the change in motion. So because it is moving in this direction, so it keeps or tries to, not keeps, tries to keep the object moving in a straight line. But what keeps it different or what keeps it changing? And of course that is the force that is inside the string here, yes? Or you can say the net force inside the string, of course, would keep changing the direction of the motion of this ball. Of course, you can see here that it makes this mass to move in a circle here. All right, so we can say this force that keeps the object moving in a circle, of course, using Newton's second law of motion, it is equal to what? It is equal to or what is Newton's second law of motion? Newton's second law of motion equals to force equals to mass times acceleration. But because we have circular motion, so in this case, the acceleration that we have a mass, and the acceleration that we have, it is called centripetal acceleration, yeah? And it is always directed towards the center of the sphere. What about the force that keeps changing the object to move in a circle? That force, of course, we call it centripetal force here, okay? So centripetal force is basically the force that keeps the object moving in a circular path. Or you can say, what does, we can ask a question, what does the centripetal force do? Centripetal forces normally keep the object moving in a circular path. So this net force here on the object, it is directed where? Directed towards the center of the sphere. So if I redraw this one for you here, okay, so when we have an object that moves, let's say, in a circle, we have covered, or we went through this, we said that whenever an object is moving in a circle, of course, let's say there is a tangential speed, and if the volley is changing, we can have tangential acceleration, and the acceleration that is, or it has happened, or we have due to the change in the velocity, it is called the direction of the velocity, let's say, due to the change in the direction of the velocity is called centripetal acceleration here. So, but remember this, we cannot have acceleration without a force, yeah? So the force that maintains the object or keeps changing the direction of this motion, let's say, or keeps it in a circle, that is called centripetal force, which is also directed towards the center of the circle here. So remember this, using Newton's second law, of course, now we can say centripetal force equal to mass times centripetal acceleration. Very good. Okay, so and here are the equations, of course. That is the acceleration of an object that is moving in a circle, let's say, okay, due to the change of the velocity's direction, let's say. So, and one more thing that we need to know. What happens when this, we said there is this mass, all right? This object that is attached to the string, and of course we make it move in a circle. And the force that keeps the object moving in a circle, we call it centripetal force. But what will happen if this force cut or vanished, or this force doesn't exist anymore? Let's say here's the mass that we have, of course. You can see here at a point here and then at a point here. What happens if this force, and of course this force, it is inside basically, or you can say it's provided by the tension that is inside the string. But what happens when this tension, let's say, or this force vanish? Remember, if this force vanishes or doesn't exist anymore, do you think the object will keep moving or stays moving in a circle? The answer is not. Why? Because we said there is a force that keeps the object moving in a circle. So if this force doesn't exist anymore, then what do you think will happen? The object will start moving in a straight line. You can say tangent to the object's circular path. So here's the circular path. The object will move tangent, or it will continue, let's say, in a straight line tangent to the object's circular path. But why will it move in a straight line? Remember, it is because of it is inertia. Inertia keeps the object to move in a straight line here in this case, okay? Because there is no force to bring it back or to change its direction, so the object starts to, let's say, go off in a straight line. All right, so now we've learned a little about centripetal force. So how can we define centripetal force? Yes. All right. By the way, centripetal force is not a new type of force. Yeah. Centripetal force is just, you can say it is, like the resultant, or you can say the effect of other forces. When other forces make objects move in a circle, then we say we have centripetal force. But remember, centripetal force is not a new type of force. It can be provided by other types of forces. So how can we define centripetal force? We can say centripetal force is basically the resultant effective force on a body that moves, or you can say on a circle. So it is the resultant effective force, yeah? So that means it is the result of other effective forces when objects move in a, or you can say when objects move in a circle, of course. And we do know that all forces are measured in Newton. Very good. So one more time, centripetal force, it is the resultant effective force on a body that moves in a circle, and of course circular path that is directed. Don't forget, the direction of centripetal force is always directed towards the center of the circular path, and of course measured in Newton. So we do know that centripetal force equal to what? Using Newton's second law we just mentioned, yeah? Let's use a different color. All right, so Newton's second law of motion, of course, equals to mass times acceleration. That is for translational objects when objects move in a straight line, yeah? Very good. The bigger the force, you can say, the bigger the acceleration. And of course, let's say the bigger, keeping the force constant, the bigger the mass, the less the acceleration. All right, but when objects move in a circle, of course, instead of calling it this one just a force, we call it centripetal force. Why? Because it is the force that keeps object moving in a circular path. And then the mass will be the same, and instead of acceleration, we will have centripetal acceleration. So remember this. This is Newton's second law of motion, but in circular motion. That'll be in translational motion, you can say, yeah. And this one for circular what? Circular motion. All right, but you already learned about centripetal acceleration, yes? We do know that centripetal acceleration equals to what? Equals to tangential speed squared divided by the radius. That is one of the equations. What if we don't have tangential speed, we have angular speed, let's say? Then in this case, we can say centripetal acceleration equals to what? Equals to radius times omega squared. All right, very, very good. What about, and by the way, we've also learned that tangential speed equals to what? Equals to radius times omega, yeah? Or omega times radius, because we're going to need this one as well. So what happens when I substitute these equations? What happens when I substitute these equations into our main equation here, or Newton's second law? So we can say centripetal force, let's use a different color. So now we can say centripetal force equal to mass times. Instead of acceleration, I'll just use centripetal acceleration, I'll use that equation above, yeah? So we'll say tangential speed squared divided by the radius. So if we call this one the first equation, now of course we can use the second equation here. When do we use this? If tangential speed is given, let's say, or been asked, and of course given other information that is needed, or other values that we have in the equation. All right, now what happens if we don't have tangential speed? Let's say we have angular speed. Then of course we can say centripetal force, let's use a different color. We can say centripetal force, okay, equals to what? Equals to mass times, instead of, remember, tangential, I'll use this equation here, or substitute this into the main equation. So we can say mass times radius times omega squared. Very good. So now this is going to be the third equation. Let's use black this time. All right, so here's going to be the third equation. All right, by the way, we can use another equation, which is very, you don't need it, to be honest, that much, but just in case, for example, let's say, what happens if I make this R the subject? R equals to tangential over omega, yes? All right, now what happens if I substitute this R into this equation? Then of course we will get centripetal force equal to mass times tangential speed over omega multiplied, or let's say times what? Let's go back one more time, times omega squared, yeah? 1 squared will be cancelled out with 1 here, so what are we left with? We're left with mass times v tangential times angular speed as well, yeah? So this is going to be another equation. You're unlikely need to use this equation, but just try to know, at least you have, or you can have something like this as well. So now, what are the equations that you're required to know? This one here, force equal to mass times acceleration for centripetal. So centripetal force, centripetal acceleration, yes. Centripetal force, once again, equals to mass times tangential squared over the radius. And of course, centripetal force equals to mass times radius times omega squared. And of course, you can have this equation as well. By the way, you know that forces are basically measured in what? Forces are measured in Newton normally. Okay, now, let's say, but we didn't talk about the direction of centripetal force much, and like what would be the relation between this and let's say tangential and tangential acceleration as well. So we've learned that when an object moves in a circular path, of course we have tangential speed, yes? If this volley of speed, of course we can have centripetal acceleration as well, because this volley, or you can say the direction of the speed constantly, the direction of the velocity is constantly changing, yeah? So of course we can have centripetal acceleration as well. Okay, now if this value of the speed increases or decreases, what else can we have? And of course we can have tangential acceleration as well, yeah? Very good. But then, one thing that, remember, the direction of the velocity doesn't change on its own, yeah? In order to change the direction of the velocity, we have centripetal acceleration. So you can see here, the direction of centripetal acceleration and centripetal force are both directed towards the center of the circle, and these two, if we have them both, then of course these two are in the same direction in terms of, let's say, if the motion is counterclockwise, let's say, and if it is accelerating or speeding up, yeah? And of course this too would be opposite if the motion is counterclockwise, let's say, and the object is slowing down, then the angle between the two would be 180. Let me tell you what I mean by this. We do know that we can say if the object's speed is changing, then of course tangential speed and, let's say, tangential acceleration and tangential speed, these two are parallel to one another. In another word, we can say the angle between the two is 90 degrees. That is, remember this, in terms of speeding, let's say, if the rotation is clockwise and it is speeding, the direction between, oh my bad, these two are parallel, my bad, okay? These two are parallel, so you can say the angle between the two is 0 degrees, yeah? Very good. That is if let's say the motion is clockwise, counterclockwise, and then the motion is speeding up, yeah? But what if the motion is counterclockwise, let's say, and the object is slowing down? Then of course the angle between the two is going to be 180 degrees. We have talked about this before. Okay, now what about the centripetal acceleration and centripetal force? You can see here. Now of course centripetal force, you can say it is parallel to centripetal acceleration, or you can say the angle between the two is 0 degrees here. But if we do something different, if I ask you what about the direction between centripetal acceleration and tangential acceleration, or centripetal acceleration with, let's say, tangential speed here. So we know that the direction of centripetal acceleration, let's say, it is perpendicular to the direction of what? Of tangential speed. And of course, tangential acceleration as well, if we have it, yeah? Or you do know that this symbol, it means the angle between these, as basically this two is 90 degrees, whether if it is with this, with the tangential, or with speed, or with the tangential acceleration. All right, what about centripetal force with this two? And of course that is the same thing, yeah? We can say the angle between the centripetal force and the tangential speed is going to be 90 degrees, yeah? The symbol means perpendicular, yeah? Very good. And of course we can say, how about the angle between centripetal force and the tangential acceleration? That is also 90 degrees if we have tangential acceleration. Remember, if the object is moving in a circular path at a constant speed, at a uniform speed, if the magnitude of speed, let's say, doesn't change, then there is no tangential acceleration, because initial, let's say, tangential speed and final tangential speed would have the same magnitude, then the tangential acceleration will be 0. But just remember this, that the centripetal force and centripetal acceleration, these are both directed towards the center of the circle, and these two would be perpendicular to these two if we have them both, if not at least to the tangential speed there. Okay, so we did talk about these, yeah? Now we did say this is the main equation. Basically we can substitute these values into the equation, we get this, and then of course the other equation that we talked about as well, which we said you're unlikely to use that one too. All right, so what does the centripetal force do? Now, this is something very important. Remember, centripetal forces keep the object moving in a circular path. In another word, without centripetal force, the object will not be moving in a circle. Okay, remember this. Okay, and also remember this, centripetal force is not a new type of force. It is just the effect of other forces. When other forces let's say keep or make the object move in a circle, then of course the effect of that force can be called centripetal force. Okay, now what happens if the centripetal force vanish? I think we did talk about this, yeah? So if centripetal force vanish, let's say, then because of the inertia of the object will tend to move, let's say, in a straight line tangent to the object's circular path. That is, if it was something like this. Let's say we have this object, yeah? And then let's use blue. All right, so we have this object, let's say this string here is cut, yeah? So what do you think will happen? Then this object here that was moving in a circular path, of course, let's say now there is no force, there's no more centripetal force, yeah? Then this object tries to keep moving in a straight line. You can say, why? Because of inertia. Or you can say, this object will move in a straight line tangent to the circular path because of it is inertia. But we do know that the object will not move in a straight line forever, yeah? After some time, gravity would pull the object downward, so you can say the object will move in a trajectory path, you can say, yeah? That is because of the effect of gravity. That is if the string is cut at, let's say, this point, yeah? But what happens if you are, let's say, reeling the object vertically, remember, vertically, and then the string is cut at this point? Then, of course, you do know that this mass tries to go in a straight line tangent to this, yeah? But what do you think will happen eventually? Of course, the speed of the object slows down until it reaches the highest point where you can say final velocity becomes 0, yeah? When it is 0, then the object starts to go down, and of course, due to the effect of gravity there. Okay, now, so what do we conclude from this? We are concluding, or we can say, as long as there is centripetal force, the object will move in a circular path. But the moment that centripetal force vanish or cut or doesn't exist anymore, then the object will no longer moves in a circle. Okay, now, what force allows the race car? Before answering this question, I would like to tell you what are. We said centripetal force is not any type of force. A centripetal force will be provided by other forces. Yeah? So what are some forces that can provide centripetal force? Yeah? And of course, we can say forces that provide centripetal force, or you can say centripetal force, centripetal, right? Centripetal force can be caused by these type of forces. What is the first type, or what are some forces that can cause or provide centripetal force? The first one we can say tension. What force? Tension force. What do we mean by tension? Let's say, let me see if I have something I can show you. Okay? When we have an object, let me see if I still have it. Okay, yes, I found it. Very good. So let's say we have this mass, all right, that is attached to the string here. So when you're trying to roll the object, move in a circle, so of course now you can see here this mass is moving in a circle. Why? Because of this tension, yeah? So we can say the tension in this string will provide enough force to keep the object moving in a circle. So we can say centripetal force, the force that keeps the object move in a circle, is provided by the tension inside the string here. Okay, so we can say tension can provide centripetal force here. Now that is one, yeah? Another type of force that can provide centripetal force, we can say what? We can say frictional force. Frictional, or just friction, let's say, or let's say frictional force. Frictional force can also provide centripetal force. What do we mean by this? Let's say we have a race car that moves in a straight, let's say in a circular path, yeah, or on a racetrack. Here is the car, let's say, yeah? And of course, this is the direction of the motion. So now this, or you can say the car is moving, so of course it has, let's say, omega, or let's say angular speed, all right? So now we do know that there is tangential speed tangent to the circular path as well, so you can say vt, yeah? And of course, we have centripetal acceleration, which is directed toward the center of the circle as well. But you can see here, right, what helps the car to change direction here. For example, at a point here, you can see that the car would have changed direction here. And the reason why, or what have caused this car to be able to make a turn, imagine, what do you think will happen if the road or the track was icy, let's say, or if it was covered with snow? Do you think the object or this racing car would be able to make a safe turn? The answer is no. Then what would happen then? Of course, the car would slide, let's say, in a straight line tangent to it is, or tangent to the circle. So we can say here, the force that provides the centripetal force here is basically friction here. So friction between, but remember this, something very important, yeah? The force that allows the race car or the car to be able to make a turn It is the friction between the tire of the car on the road, okay? What if the question were, let's say, the driver of the car, yeah? That would be a total different question here. Let's say the driver sitting inside the car. What keeps the driver to move in a circle? That is, of course, you can say the force of friction between, let's say, the seat, let's say, and the seat belt, and of course, he's holding the steering wheel. That could also provide, or add up to the friction between, let's say, the car and the driver, so that the driver can move inside, let's say, can move in a circle inside the car here, all right? Or let's say can continue moving in a circle, which is basically inside the car in this case. Okay, so in this case here, we can say the friction between the tire and the road here. Imagine if this is the car, let's say, and of course we know that gravity or force of gravity, Fg, would be downward, Fn normal force would be upward, yeah? So that is if we look at the side of the car. But the force that keeps the object moving in a circle, of course, that is frictional force, you can say. So frictional force here would provide the centripetal force, or the centripetal force necessary, or enough centripetal force, let's say, to keep the object moving in a circular track. So the second type of force that can provide centripetal force is, you can say, friction. Another type of force here we can say is gravitational force. Gravitational what? Gravitational force. And how do we know gravitational force provides centripetal force? Now I want you to think about the motion of the sun, let's say, or the motion of the earth, not the sun. The earth moves about the sun, yeah, in a circle. But what keeps the earth moving, let's say, or revolve around, orbit around the sun, yeah? Let's say this is the sun and here's the earth, yeah? The earth, let's say, wants to go like this. At a point there, it might want to go in a straight line, but gravity keeps, let's say, pulling the object towards the center, yeah? And of course, so we can say the force that is providing centripetal force here is basically the gravitational force. Another force that we can have is, you can say, magnetic force, yeah? Another type of force, magnetic force. How can a magnetic force provide centripetal force here? Later on, of course, in, let's say, Unit 5, you will see that when an electron, let's say, or a proton moves into a magnetic field, of course, it experiences a force. And of course, this force will keep the object moving in a circle, whether if it is clockwise or counterclockwise. It depends on, let's say, the charge of the charge of, let's say, or whether this charge is positive or negative, and of course the direction of the magnetic field as well. So based on this, or you can say magnetic force can also provide centripetal force as well. And another type of force we can have, you can say electrical force, yeah? Electrical force. How can an electrical force provide centripetal force? Now think about the electrons. So electrons orbit around the nucleus. We do know that electrons are negative. The nucleus is positive. Yeah. So of course the force between the two, or this electrical force, makes the electrons revolve or orbit around the nucleus without letting the electrons to move away from the nucleus. Let's say just easily, unless if there is another external force here. So these forces, of course, can provide centripetal force. Let's say, so that objects can move in a straight line. Tension, frictional force, gravitational force, magnetic force, electrical force, all these type of forces. There is another force, actually, that is left. We can say normal force as well, right? How can a normal force provide centripetal force? You will see later on, of course, we'll solve, let's say, if in a cylinder, let's say, of the amusement park, later on you will see that, okay? This cylinder would be rotating or moving in a circle. Then of course you would see that if the person, for example, is standing there, of course they will drop the bottom, let's say, under their feet. So Fg would be downward, let's say, friction would be upward here in this case. And of course the back of this person will be pushed against the wall, and then the wall will have a reaction, or you can say Fn, and of course this Fn would be directed towards the center of this cylinder, keeping this person, let's say, or keeping the person moving in a circle. And of course, Fn in this case, of course, would provide a centripetal force as well. There's other examples of this. You can say, let's say, when people write on the, let's say, wall of death, you can say, yeah? And of course, that would be another example. But here, instead of you standing, of course, you can have your motorbike or, let's say, bicycle moving in a circle without ever been falling down. But of course, in order for you to be able to do that, you need enough, let's say, angular speed for you to keep yourself moving in a circle. So these are the forces that can cause or that can provide enough centripetal force so that the object can keep moving in a circle. So now we can go to these questions here. The first one says, what force allows a race car to travel in a circular path on a racetrack? What force allows a race car, not the driver here? So of course, in order for the race car to move in a circle, there must be a force of friction between the tire and the road. So in this case, we can say the force of friction provides centripetal force, yeah? Or the force of friction between the tire and the road provide enough centripetal force so that the race car can move or travel in a circular path. What force keeps the moon in orbit? Yeah, remember, not only the Earth moves around the sun, moon can also orbit the Earth. Yeah, so what force keeps the moon, or what force keeps the moon to orbit the Earth? And of course, that is gravitational force. So we can say gravitational force provides centripetal force so that the moon can move in a circular path. And of course, we have these study tips. These are very important. Make sure you go through them as well. It says what? In a circular motion, the centripetal acceleration is in the direction of centripetal force. We do know that, okay? And then towards each one of them is towards the center of the circular path, and both are perpendicular to the tangent velocity of the object. We did cover, or we talked about this one as well. Something also very important is this. The second point, very important. I want you to know that. Know this. It says an object in a circular path will never be in equilibrium, and I want you to ask yourself why. If an object is on a circular, let's say, path, why it will never be at equilibrium, right? The reason is this, because we do know that when an object is moving on a circular path, let's say, the direction of this, let's say, speed is or velocity is changing. Yes. Now there might be, let's say, the magnitude of this velocity doesn't change. Or it keeps moving, let's say, in a circle, let's say 120-meter road, yeah? The speed of this car is 100 kilometer per hour, let's say, yeah? And this body doesn't change. It always keeps moving, let's say, at 100 kilometer per hour. So, of course, there's no tangential acceleration because the speed doesn't change. Okay, but why the object will never be at equilibrium? And that is because you can see here, at an instant, the object's direction is this way. At another instant, the object's direction is on the other way, yeah? And then you can see the direction of this, let's say, velocity keeps changing always. Now, let me ask you a question. Can the direction of velocity of an object move unless there's no force acting on the object? The answer is no. Objects will always tend to move in a straight line, but when there is a force, then their direction will change. So we can say this. The direction of the velocity can never, ever change unless there is a force on it, all right? So you can see here, or a net force on it, yeah? So you can see here the direction of the velocity is always changing. If that is the case, then that means there is always a net force acting on the object. And if there is always a force acting on the object or a net force, that means the object can never be at equilibrium. Once again, the object can never change direction if it is at equilibrium. It will always stay in one direction, right? But as long as the direction is changing, that means the object can never be at equilibrium. Now we have another question here. It says, question 17 says, imagine that you attach a heavy object to one end of the spring, and then, while holding the spring's other end, roll the spring on the object in a horizontal circle. Does the spring stretch? Why? Discuss. You answer in terms of the force that maintains circular motion. Now, at this point here, we have a spring, okay? So let's say here's a spring here, okay? Now, at the end of the spring, there's a mass attached to the spring. And of course, you're trying to move this mass into a circle, yeah? So what do you think will happen? Then, of course, you will be able to move this one. So let's say here is a spring at an instant, yeah? But as you try to make the object spin or not spin, move in a circle faster, what do you think will happen? Right? Now, we do know that the omega, or the angular speed, is going to increase. If that is the case here, then of course, you can say there's also a bigger moment of inertia, where you can say the tangential speed will increase, of course, yeah? So, of course, bigger tangential speed, that means bigger tendency or moment of inertia to keep the object moving in a straight line. But then, because you're trying to move the object in a circular path, so what keeps the object to be pulled back towards the center? That is the spring, yeah? So as you do that, or you can say, once you're moving it fast in a circle, you need a bigger force to bring the object back to the, or towards the center. Because the spring is elastic, so the spring, of course, it can stretch here. So, of course, the faster the speed of rotation, you can say the more and more it will stretch because it needs a bigger force to keep or to change the direction of the speed in this case, and makes it or keeps making it directed towards the center. So we can say here, yes, okay, the spring stretch. Why? Because the centripetal force required to keep the object's circular motion is transmitted, yeah? Transmitted what? Through the tension of the spring. And of course you need a bigger one, yeah? A bigger one, that means more stretch, and more stretch leads to extension, all right? Very good. Now we have another question which is also important. Question 18 says, why does the water remain in a pail that is drilled in a vertical path as shown in the figure below? Now that is, this is also very interesting. Take a look. We've all, most of us have seen this one, yeah? Let's say we have a water that is in a bucket or a pail, you can see here, and then you are given it enough angular speed so that it can move in a circle, yeah? But then at the highest point here, you can see, then this water, right, does not come out from the pail or from the bucket. And do you know why? I believe, all right, let me tell you why, okay? That is because when these two objects are moving, you can see here, so the bucket and the water itself, they're at both, yeah? Have what? Let's say, have the same moment of inertia, you can see that, because these two would be moving together. So moment of inertia tries to, let's say, this path of inertia, yeah? So inertia. All right. So you can see here that these two would be both, or you can say because of inertia, which is the tendency of an object to, let's say, keep, or the resistance of an object, let's say, to the, how can I say this? Basically, inertia is basically the resistance to the change in the object's state of motion. So the object's moving at a point here. So you can see the direction of the motion is, you know, like, let's say, to the right, to my right in this case, yeah? So moment of inertia tries to keep the object moving in this case, yeah? And of course, we do know that there is gravitational force that is trying to pull the water downward, but also towards the center, that is centripetal force as well, yeah? And of course, you can say we have centrifugal force as well. That is, I'll be explaining this one later, you can see, all right? But what is important here, when these two objects are, let's say, the highest point, these two are basically, of course, there is gravitational force here, but the gravitational force, Fg, for these two would be the same thing. So if these two are falling, these two would be falling simultaneously or together. So, of course, you can see that no water is coming out of the bucket here. Now, regarding this, I might give you an example, maybe not exactly related, but hopefully it can give you an idea of how it is. Let's say that you and your friend are both sitting inside a train and the train is moving at 100, let's say 200 kilometers per hour, yeah? Now, for you and your friend, let's say, of course, none of you is moving, let's say, further apart or let's say faster than the other one. That is because both of you are sitting inside the train, yeah? Okay, so the reason why here it would be something similar perhaps to this, maybe not exactly the same. The water doesn't come out because the water is moving with the bucket. If the bucket is falling, the water would be falling with the bucket. So these two are moving together. Once they're moving together, the water doesn't come out. And of course, I can, I have a video if I can, let me see if I can show you this, right? To help you understand better of what I mean by this. Okay. So here's bucket of water. Take a look. Now here's the bucket, and of course we pour some water into the bucket, and now we're giving it enough, let's say, angular speed so that we can make the object move in a circular path, right? So enough speed. So take a look here at the highest point. Let me, all right, let's go back a little and make this one at the highest point here. Okay, not this. Let's go back a little. All right, I want to pause this one at the highest point. All right, perhaps somewhere there, too much. Okay, take a look here. Now what we have, or as you can see here, let me get this. Okay, so as you can see here, right, at the highest point, gravity is, of course, pulling this two downward, yeah? But gravity on the bucket and on the water is the same in this case. So if these two are falling down, these two would be falling together. So, of course, you would see that no water coming down. And the reason why, you can see, by the way, you can see that also the bucket and the water would also have the moment of, you can say, inertia as well. So the tendency to move in a straight line. So what keeps them to move in a circle? That is, of course, the tension inside the rope, or the rope here, which in this case, the tension inside the rope would provide the centripetal force to keep the water and the bucket to move in a circle. But once again, why the water doesn't leak, or why we can move this through without, let's say, without water leaking, that's because the water tends to move in a straight line due to straight path due to inertia, while the people on the water have the same acceleration. Don't forget, yeah, the same acceleration, and of course, they do not fall down. Or you can see these are not, or the water is not coming up. So they have, you can say, they all have the same tangential acceleration, centripetal acceleration, and centripetal force as well. Okay. Now, we have a sample problem, of course. All right, what does it say? It says a pilot flying a small plane 30 meters per second in a circular path with a radius of 100 meters per second, 100 meter. If the force, if a force of 635 newtons needed to maintain the pilot's circular motion, what is the plane's mass? Yeah, very, very good. Take a look at the information that is given. You're given let's say the speed, okay, or tangential speed. Let's say you're given the radius. You're given the force. Yeah, how can you find the mass of the plane? Of course, because we're given tangential speed, so of course we can use the centripetal force equal to mass times tangential speed square over the radius. Yeah, we want the mass, so make the mass of the subject. You could cross multiply. So mass equals to what? Centripetal force multiplied by the radius divided by what? Divided by tangential speed squared. Yeah, tangential speed squared. And of course we want to find. You just plug in the numbers. Yeah, the force is 635 times what is the radius? The radius is 100 meters. Yeah, and then divided by the speed square, which is 30 squared, and then of course you can find the answer, which is about 70.6 kilogram, and that would be the mass of the plane. That is for this sample problem. Take a look at the second one here. All right, what does it say? It says a 905 kilogram car travels around a circular track with a circumference of 3.25 kilometer. I want you to be very careful when you hear or when you see the word circumference here. All right, so we have a circumference of what? Of 3.25 kilometers, okay? All right, and magnitude, or what else? If the magnitude of the centripetal force, so we have centripetal force, which is this much, and here is the mass, yeah? It says, what is the car's tangential speed? Okay, so very good. Now, because they're asking for tangential, so centripetal force equal to mass times tangential speed squared over the radius, yeah? Then, of course, we want tangential speed. So tangential speed squared equal to force times the radius divided by the mass, yeah? So we do have the centripetal force, yeah? We do have the centripetal force, which is 21, which is what? Which is 2140 Newton times the radius. Now, but here's the question. Do I have the radius? What about the mass? I do have the mass, 112, yeah? But do I have both? The answer is no. So why do you think they have given you the circumference? They have given you the circumference for one reason only. And remember this, whenever they give you the circumference, there is only for one purpose. And the purpose is to find the radius. So how do we find the radius in this case? We'll say circumference of, by the way, circumference of a circle equals to 2 pi r, yeah? So we can find the r, radius equals to circumference divided by the 2 pi. By the way, the circumference is 3.25 kilometer. Instead of kilometer, we can write 1,000 here, or for, in this case, it becomes 3,000, becomes what? It becomes 3,000 let me get the pen back, all right? It becomes 3,250 meter. Now, of course, you can say 3,250 divided by 2 pi, and of course, you will get, or you will, the radius becomes 517.5 meter. That is the radius. Now you can plug in the radius into the equation, yes? And then, of course, we can find the answer then. So the radius is 500 what? 517.5. Now, multiply this, divide by 905, and then, but by the way, what we have found is basically the tangential speed squared, yeah? We don't want tangential speed squared, so whatever the answer there, you can take the square root for both sides, yeah? These two will cancel out, so tangential speed squared will equal to what? So it'll equal to 35.0, you can say, meter per second because it is tangential speed, okay? So 35 meter per second. All right, I'm afraid that is all for now, right? Next time, inshallah, or in the next video, we'll continue starting from question 21. Till then, keep practicing, and I'll see you next time. Assalamu alaikum wa rahmatullah.